Okay, here's a projectile motion problem, and we've got a pool ball that leaves a table with an initial velocity of 2.4 meters per second. Predict the time required for the pool ball to fall to the ground and to fall to the ground and the horizontal distance between the table's edge and the ball's landing location. So I'll say for myself that the first thing that I do anytime I try to attempt these problems is to attempt to understand what's going on by drawing a picture. So I would say, okay, I've got some sort of table. I'm going to draw it over here. And I know this table has a height of 0.6 meters. 0.60 meters, by the way, the 6 is significant. This 0 to the right here is not significant. So we have one significant figure. So we have 0.6 meters, the table. Let's say this is some sort of, ground here. And we've got on this table a pool ball that is leaving the edge of the table somehow, and it gives an initial horizontal velocity and it gives the value. Now it's asking you to find a couple of things. One is the time required for the pool ball to fall to the ground. So what we're trying to find is the t for the ball to hit the ground. And then what else? We are also looking for the horizontal distance between the table's edge and the ball's landing. So if this is the table's edge here, this is the table's edge, we know that the ball is somehow coming off the table with some sort of horizontal velocity, 2.4 meters per second. And we know that that ball is going to fall because it's a free fall from gravity. And at some point, it's going to hit the ground. Now, if in order to start this problem, I think to myself, okay, I got to start somewhere. I want this time that it takes to hit the ground, and I wanted this distance. Well, in my mind, I'm thinking, how am I going to approach this problem? First of all, I need to know how long it takes to get to this bottom here. Now, what I'm thinking to myself is it's a free fall, essentially. Even if we didn't have this horizontal velocity, this ball would be, it's like we dropped the ball from a height of 0.6 meters. It's just falling this way, even though it has a constant velocity in this direction. So I know that it's in a free fall, and the acceleration of the free fall, I know, is the acceleration due to gravity. So I know that there is an acceleration in this direction. The acceleration is equal to 9.8 meters per second squared. Now, since I'm going to have to deal with measurements, one of the things I like to do right away is to to establish a coordinate axis from which to measure. So let's say I want to just look at this first part, the free fall. Well, I think what I'll do is I'll put an axis this way. I'll say this is the 0 point. I'm going to call this y. I'm going to say y equals 0. And I'm going to measure y in this direction. Now, I need to tell myself, is this going to be my plus y direction or my minus y direction? And I'll just say for myself, I think it's easier in this problem, since I'm just trying to get this distance here from here to here, to call this plus y. So I'm going to call this plus y. If I call this plus y, that makes my acceleration in the y direction equal to 9.8 meters per second squared. Notice it's not negative 9.8 because I've defined positive y in this direction. So now I say to myself, well, this is kind of a simple problem. I start out with the velocity in the y direction is nothing because it's just a free fall. So I just basically draw, even though it has a horizontal velocity at the outset, it has no vertical velocity. So Vy is 0, and I know that equation, I also know that y equals 0. That's the initial y equals 0. And I've got a few equations that I can call on. What are those equations? Well, if we have a constant acceleration, we can see that these are our two equations, that the final distance traveled equals the initial distance, the starting point, plus the initial velocity times time, plus 1/2 acceleration times time squared. The v final is v initial plus acceleration times time. Sometimes instead of initial, you'll see v naught. Now we're going to go. Okay, so the equation that we're going to use here is f final, or in this case it's going to be y, so I'll go ahead and use y. Y final is y initial plus v naught times time plus 1/2 at squared. Now remember, we're measuring from this 0 point of y here in the plus y direction. So our acceleration is in the plus, the acceleration y is in the plus y direction. So we can, from this equation, we know that the initial velocity is 0. So this term drops out, and we know that the initial y point is 0, y equals 0. So we're left with this equation, y final is equal to 1/2 at squared. And we're looking for the time it takes to hit the ground. So we can rearrange this equation to get basically that 2 times y final is equal to, or divided by a, is equal to t squared. So, and we can take the square root of that to solve for t. So t is equal to the square root of 2 times 0.6 meters divided by, I'm going to say 10 meters per second squared. I could use 9.8, but I only have one significant figure with the height of the table, so I'll just still keep one significant figure with the acceleration of gravity. So what we have here is t is equal to, 2 times that is 1.2 over 10, makes that the square root of 0.12. Meters drop out, so 0.12 seconds squared. So time, whoa, that is not much time. Time is the square root, bring out the seconds, the square root of 0.12, which is equal to, what is that? 0.3, 0.9, 0.4, 0.16, between 3 and 4. So I'm going to say like 3.5. Oh, I only have one significant figure. Is it closer to 3 or 4? I don't know. It's between 3 and 4 seconds. So that's how long it takes to get, for this guy to be in a free fall and hit the ground. That is not, well, 3 or 4 seconds. That's not too bad. No, excuse me. Something wrong. 0.3 and 0.4 second, between 0.3 to 0.4 seconds. When I square 0.3, I get 0.09. When I square 0.4, I get 0.16. I think it's closer to 0.4. I'm going to call it, with one significant figure, I'm going to call it time equals 0.4 seconds. Now, I'm going to use what do you call it? I'll be back. I'm going to use a calculator to see how wrong that is. Okay, I just found out it's equal to 0.35, actually 0.346. So this would actually round down to time. One significant figure, time is equal to 0.3 seconds for one significant figure. It's so it feels uncomfortable to lose what we imagine as accuracy. So I might report that to 0.35 seconds. Okay, so what's next here? We figured out that it took 0.35 seconds to drop from here to here. And now we want to know how far does it go. Well, now we're left with a very simple task of computing the distance that it travels when the velocity is this initial velocity 2.4 meters per second. So let's see, we know 3.5 seconds and 2.4 meters per second. So I'm going to go. So the velocity, the distance, excuse me, a distance in the x direction, now we're looking at traveling in this direction, and now we have a different set of axes. We have the x direction, if I call it that, the plus x here, like this. We know this guy is gonna drop down to the ground, but it doesn't matter. We have a constant, theoretically, velocity in the x direction equal to 2.4 meters per second. So the distance, x of f, is equal to xi, which is equal to 0, xi, plus v naught times the time. We would add terms for acceleration, but we know that we have no acceleration going on, so now we just have it reduced to this equation right here. So the final distance is equal to, this we know it goes to 0, is equal to basically 2.4 meters per second times the time, which is 0.35 seconds. I'm going to keep this significant figure here. It just feels so bad to lose one. So I've got that times 2.4 meters per second. It gives me x sub f is equal to 0.83. The seconds cancel, and I'm left with meters. So, or one significant figure is equal to 0.8 meters.